Thank you, Miles, for the introduction. It's a pleasure and an honor to be speaking here. Actually, I'm right now not in Leipzig, but I'm at the ETH in Zurich for some time, where I give a course. And so the title shows kind of the main content. It's about optimal transportation, which by now is a classical subject. And Michael Goldman, who now is in Paris, he was at some time also postdoc in Leipzig, and I started a while ago. And by now, together with Martin Huisman and Tatsuya Miura and Maxime Prodhomme and Tobias Ried, we have a couple of extensions. I perhaps have a chance of mentioning this. So this is one first busy slide where I tell a bit for the experts what this is about, but then I will take enough time to remind you of what optimal transportation is, why this relates to the Monge-Ampere equation, what the main ideas are. So those who don't know things so much on this page don't get kind of deterred too much. So essentially, in a nutshell, one might say that we're following the old philosophy or approach of Di Giorgi to the regularity of minimal surfaces, where, if for those who know that area, the harmonic approximation is kind of a key step. So a key step in doing this regularity theory is to show that a minimal surface might be locally well approximated by the graph of a harmonic function. And since harmonic functions, the regularity theory for harmonic functions is almost trivial, that's kind of the way to get the foot into the door, by kind of lifting the obvious regularity theory for harmonic functions to minimal surfaces. So the harmonic approximation is really a key step in the setup. And in a certain sense, we'll do exactly the same thing. We'll approximate the displacement by a harmonic gradient. And once you do this, once you have the harmonic approximation set up, then this feeds into a kind of more or less general theory, which gives you what's called a one-step improvement, which feeds into what's called a campanato iteration, which gives what's called epsilon regularity, and then may also yield partial regularity. And the outcome here in case of optimal transportation is a kind of an epsilon regularity theory, which leads kind of a C2 alpha, so a Helder space regularity for up to the second derivatives for the potential in optimal transportation. I will remind you of that, what that is, which means is a C1 alpha regularity theory for the map. And so I'm stressing that this is, that the novelty is not so much in the results, but in the approach, which in our case is purely variational. So there will be no maximum principle. So it completely bypasses the celebrated regularity theory by Caffarelli. And their applications are kind of old and new. The old applications are related to what's called partial regularity and kind of take up work or reproduce with a different proof work by Figali and Kim and De Filippis and Figali, also regularity theory up to the boundary by Chen and Figali. But it also allows to do new things, which is related to the so-called matching problem. And perhaps I have the time of saying something about this. So this was kind of a brief outlook of what the main subject is of the talk. And now I slow down and remind you of what optimal transportation is. So optimal transportation is a way of relating to non-negative measures of equal mass. So with loss of generality, think of probability measures, mu and lambda and RD. And in a certain sense, it's called optimal transportation because you should think of these masses as being made out of tiny particles, and you really ship particles from one place to the other. And you want to do it in a so-called optimal way, which is a variation problem which already Monge came up with. And the modern formulation by Kantorovich is measure theoretic. And what you're looking for is a so-called transfer plan pi, which lives on the product space. And it has its first marginal mu and its second marginal lambda. So it's a way of coupling these two probability measures. And then you're optimizing, you're minimizing the transportation cost. So the squared Euclidean distance by which you ship the infinitesimal mass, which is sitting at a point X, to the infinitesimal mass, which is sitting at the point Y. And the minimum of this variation problem is, at least I tend to call it the Wasserstein distance. Other people call it the Monge-Kantorovich-Rubinstein distance. So in this case, it's the square of, in fact, a metric on the space of probability measures, which metrizes the topology of weak convergence. So that's optimal transportation. So there is a connection between optimal transportation and a well-studied, highly nonlinear partial differential equation, which is the so-called Monge-Ampère equation. And this slide is to remind you of this, or you tell you the story if you don't know. So here again is the problem of optimal transportation. You're minimizing the transportation cost overall. Transportation plans pi, which have the right marginals. And let's think of the second one of being the Lebesgue measure for simplicity of this discussion, and the first one, a general measure. Then it's a consequence of purely convex analysis that the optimal pi is supported as a measure on the product space. The support on the measure is on the subgradient of a convex function psi. So a pair of points is in the support of the measure pi if and only if y is in the subgradient of psi at the point x. So it's sometimes also called cyclically monotone property of this support. And so we know that convex functions have gradients almost everywhere. So I can even write down nabla psi. And then the fact that pi has the right marginal means that, in fact, the Lebesgue measure is the push forward, as we say, of nabla psi, the push forward of nu under the nabla psi. And now if you assume everything were smooth, so in particular psi was smooth, then you could use the transformation rule on the right-hand side integral, and you could see that this condition here, this weak formulation, turns into this partial differential equation where the determinant of the Jacobian of the gradient, so the determinant of the Hessian, which is a symmetric positive definite matrix, that the determinant is given by mu. And that's an instance of a Monge-Ampère equation. And that's the connection between optimal transportation and the Monge-Ampère equation. So you may say the Monge-Ampère equation is the Euler-Lagrange equation of optimal transportation. So the Monge-Ampère equation by itself is interesting because it's kind of a very natural example of what's called a fully nonlinear PDE, in the sense that you have an equation of the form f of the second derivative matrix is equal to 0, where this function f is a highly nonlinear function. It's not the trace, it's the determinant. And but however, it's an elliptic. It's an elliptic equation. It satisfies the comparison principle. It's kind of amenable to viscosity solution methods, and therefore it's kind of very natural point of view, very natural nonlinear PDE. But however, it's not just highly nonlinear; it's also degenerate. It stops being uniformly elliptic when you get at the boundary of the set where the matrices are strictly positive definite. And this degeneracy is kind of reflected by the fact that it has a very large invariant space, meaning it's affine invariant instead of just rotational invariant, which we know for the Laplace operator. So it has a non-compact group acting on it, which is the reverse of the metal of being degenerate. But still, so as I mentioned at the beginning, there is the breakthrough of Caffarelli, who used comparison principle, affine invariance, compactness to develop a regularity theory for this equation. So therefore, I mean, looking at the variational problem for optimal transportation is interesting because in a certain sense, we're at the crossroad between a variational structure and a fully nonlinear structure. And now we will look at this side. This is a reminder that, that the regularity theory for optimal transportation is subtle. There is no reason to assume, or in general, these maps, the gradients of the convex potential have no reason to be smooth. And there is kind of almost a folklore ensemble example of this, where the two measures are just, or the densities have Lebesgue densities, and those Lebesgue densities are just characteristic functions. And one of the sets is a ball, and the other set is kind of a smoothed out version of two halves balls kind of removed from each other. And then it's easy to convince oneself that although the sets are smoothly bounded, the optimal transportation map between these two sets, and even if you would smooth out the densities, is discontinuous. So therefore, it's interesting even to develop something like epsilon regularity. So a statement of the type that if the two measures have smooth densities and if their transportation distance is small, then things are smooth. So this would be the analogy to minimal surfaces, where we know that in high dimensions, again, they're not smooth in general, but there's always this type of smallness implies regularity result. And that's exactly what we're going to do. And as I mentioned at the beginning, it will rely on a harmonic approximation result. So the fact that if we have two measures which at least locally are close to constant, and if the transportation distance is below a threshold in a suitable non-dimensional sense, then we show that the displacement, so the amount by which you ship the mass integrated against the transference plan, locally is the gradient of a harmonic function. So, so that's in words kind of the main ingredient to get started. And the next slide is exactly stating this, which is in a certain sense the core of our result, and which might be of independent interest. And I will stay with this slide and kind of slides which look very similar for a while. So there is no need to try to absorb things in one simple going. So, we're given an optimal transference plan pi between the measures mu and lambda. And we look at the local transportation cost. So here we take our kind of radius to be of order 1. So for some reason 6 appears here because in the end we end up with 1. So don't worry too much about this numerology. So we have a local transportation cost, which we control. And we have a local size of the data. So we locally measure how close our measure mu, and the same holds for the target measure lambda, how close the measure mu is to a uniform distribution kappa in this ball of size 6. And we measure in the right topology, which means we measure in the Wasserstein topology. So here we don't, these measures can be completely atomic. There's no reason for them, being smooth for the purpose of this statement. And now comes kind of a typical harmonic approximation result. So given some small number tau, there exists a threshold epsilon, which only depends on tau and the dimension d, and a constant, such that if the local energy and the local data size is below this threshold epsilon, then there exists a harmonic gradient, so meaning all the partial derivatives are harmonic functions, of which the Dirichlet energy is well controlled, such that the displacement x minus y is pretty well approximated by the gradient of this harmonic function. And here I could have put either x or y, that's a higher order term, and for justice I put the midpoint between x and y. So, so the displacement is close to the harmonic gradient, and this here is substantially smaller than the original transport energy because this small parameter tau appears in front of the E, and remember tau was just a given small number, and then there is a big constant in front of the data term. So, so in that sense, this statement states that the displacement in optimal transportation, provided you're in the small cost and small data regime, is close to harmonic gradient. So let me explain this statement a bit more in detail and comment a bit more. So the first comment is, here is again the statement, so you have still the chance to look at it. The statement states that here I want to make the point that in a certain sense the statement has the correct homogeneities, because the local transportation cost is something that's, if you want, quadratic in the solution, it's quadratic in the displacement, it's quadratic in the Brenier map. The data term is something that's quadratic, it's the square of the Wasserstein distance. And also the output we're looking at here is something that's quadratic in the displacement. So all the homogeneities of all the terms, the blue, the red, the blue term, and this blue term, and the green term, they have the same quadratic homogeneity. So it's a little bit like, the analogy would be a little bit like what you would do for a uniformly convex but non-quadratic variational problem, where you could also show that you can approximate a minimizer well by a harmonic gradient up to a small multiple of the energy and a big multiple of the data term. So so it has the right flavor for kind of a nonlinear problem. So let me now tell you a bit how we get this kind of harmonic approximation problem property, and that's an excuse to tell you a bit more about optimal transportation. Kind of, I know it's a classical field, but I think it's a very nice area. And something we use is something quite classical, namely the equivalence between the Lagrangian and the Eulerian point of view in optimal transportation, which was observed by Benamou-Brenier. And here I'm explaining, on this slide, I'm explaining to you the Eulerian side. The Lagrangian side is the one which we had in the beginning. And so this picture here refers to the Lagrangian side, where you really have kind of particles located at x, particle located at y, a transfer plan pi, and that's these two pictures refer to the Eulerian side, where you look at kind of pairs of instead of looking kind of at trajectories of particles which move in time, you're looking at pairs of density rho and flux j, which satisfy what's called the continuity equation, and you monitor what is the kinetic energy of such a pair of rho and j. And the statement of Benamou-Brenier is that the Wasserstein distance between the two measures mu and lambda, the square of it, could as well be obtained by minimizing the kinetic energy over all pairs of density flux, which satisfy the continuity equation, and which at time t0 connect the measure mu to the measure lambda at time t1. So there is kind of now some artificial time t, which goes from 0 to 1, and which kind of appears here in the definition of this variational problem on the Eulerian side. So why is it not surprising that this is a good way of looking at the problem when you want to prove regularity? So the reason for that is that while on the Lagrangian side, the problem almost looked like, or in fact was a completely linear convex degenerate problem, because you're minimizing a functional that's linear in pi over all admissible pi in a convex set. So this problem, this side of the problem doesn't reveal, at least in the Monge formulation, doesn't reveal at all anything strictly convex. The blue side, the Eulerian side, does. And the reason for that is that this innocuous looking functional you associate to a positive number rho and a vector j, this number here is a strictly convex function. It's not instantly obvious, but that's one of the things I learned from Jan Brenier a long time ago, and that's crucial. So in a certain sense, you rewrote the problem as something which with a strictly convex functionals, and that of course is something which in a certain sense gives you hope to develop a variational regularity theory. So here now is our result again, reformulated on the Eulerian version. So so now we're not looking at the map pi, at the transport plan pi, but we look at the pair of density and flux, which are related to pi by these natural formulas. And instead of writing the local energy in a Lagrangian way, we write it in this Eulerian way by integrating the kinetic energy over a finite space-time, quote-unquote, time cylinder. And then this is just, in a certain sense, a reformulation of the result. It can be stated like this. If this Eulerian transport energy is small and the data term is small as before, then there exists a harmonic gradient, so that this expression here, which relates the ratio of j and rho to grad phi, is much smaller than the than E, so kind of noise, a good noise to signal ratio. And again, this can be interpreted in a kind of mechanical way by recalling that, or by noticing that the ratio of the flux and the density, in fact, is nothing else than the velocity, the Eulerian velocity. So in a certain sense, our result can also be interpreted that the Eulerian velocity in optimal transportation in the small data, in the small energy regime, is in fact close to a harmonic gradient. And now you may already almost guess how one proves this this harmonic approximation, and that's kind of a slide to give you a rough idea of how this is done. So somehow, given the Eulerian version of optimal transportation. So we're given a pair of the density rho and a flux j that satisfy the continuity equation, and we connect at initial time our density, given density mu, to the given density lambda at the final time. And now to such a setting, we want to associate a harmonic function. And so we need, in order to define it via a Poisson problem, we need boundary data for this harmonic function. And flux boundary data, Neumann boundary data are the most natural, because in a certain sense we also have Neumann boundary data, flux boundary data for for this fluid dynamics, for this Eulerian side. Namely, if we are on a ball, on the cylinder, which has a base of a ball of radius b, radius r, then we have the mantle, the lateral boundary of the cylinder, and we can consider at the flux in and out of this boundary, so the normal component nu times j of our flux, we call this F. And so that's a flux which flows through this lateral boundary of our cylinder. And we take the time average of this flux and we call this F bar. And that's supposed to be the Neumann data of the Poisson problem, which defines the harmonic gradient. So we need to allow, we only have harmonic gradients and not harmonic function, because we need to allow for a non-zero constant here, because the integral of F bar in general will not be equal to 0. But this is how that's the simple idea of how to construct this harmonic approximation. And so that's a kind of a schematic picture, how you pass from the Eulerian side to the Poisson problem, and then back how this feeds into the Eulerian side. And you do that, you have to, when you do that, you have to choose a good radius r when you carry out this construction. So that's the idea, in the end, the idea how you relate this highly nonlinear problem of optimal transportation in its Eulerian version to the linear, kind of well-studied Poisson problem. Let me look at my watch. Okay, so I guess I still have a bit more than 10 minutes or so. Here is kind of a typical application, which I already mentioned in the beginning, namely a so-called epsilon regularity result, which just mimics the famous result by De Philippis and Figali, but now with this different proof, namely if we're given two measures, mu and nu, which come from smooth or Hölder continuous densities f and g. Let's normalize them by having the value 1 at the origin. We look in some radius r. We look at the transport distance, now written with help of the Brenier map, the map that transports one density on the other by push forward. We have the data term, which are the Hölder norms, the alpha Hölder norms, the alpha semi-norms of these two densities, properly non-dimensionalized. Here, all these quantities are non-dimensionalized in the natural way. And then the statement is, if the local energy is small enough and the data term is small enough, then indeed in a ball of half the radius, the gradient of the Brenier map is alpha Hölder continuous, and we get exactly the right type of PDE estimate with the right homogeneity, Hölder norm of grad T estimated by the Hölder norm of F and G, plus kind of an L2 type of norm. So that's a typical epsilon regularity result, which we recover from this harmonic approximation. So here again is the statement written slightly differently, this time in terms of the potential, and this is in a certain sense the main difference in the approach between De Philippis Figali on the one hand and our approach, namely is that they carry out a perturbation theory around the nonlinear equation, which is the Monge-Ampère equation with a constant right-hand side, for which they have epsilon regularity by the result of Figali and Kim, which in turn relies on Caffarelli. Whereas we right away jump to the linear equation. So we perturb around the Poisson equation. And one consequence of jumping right away, I mean, not doing this intermediate step, is that we get pretty much for free the right homogeneities in our final estimate. And we get it in one step. We don't have to bootstrap in kind of several steps. But again, I would say the main difference is that we use strictly just variational arguments, whereas they use the comparison principle in a heavy way. So it's a kind of orthogonal approach. We also, perhaps I can jump over this with Tatsuya Miura, who is in Tokyo, was also at some point postdoc in Leipzig. We have a similar result for boundary regularity, where again we get kind of the right homogeneities and the right type of norms on the right-hand side in terms of the boundary data. So, but in the interest of time, I'm going to jump over this. There is, so those are in a certain sense recovering, perhaps slightly improving existing results. The kind of a more novel application has to do with the problem of matching, which is a problem which came up in computer science. So the goal is to match the Poisson point measure, so a very singular measure where at a kind of random points, so Poisson point distributed points, you put Dirac measures. So that's kind of the measure on the one hand, and on the other hand, you put, let's say, either another instance of this measure or the Lebesgue measure, and you want to transport one and the other, and you're interested in large scales, and you want to kind of, in a certain sense, say something about the hydrodynamic limit, about local fluctuations, and that's exactly a problem where our regularity theory is quite helpful, because the harmonic approximation, which I showed to you at the very beginning, kind of can deal with completely rough measures. So whereas the maximal regularity-based result and has as a starting point the Alexandrov comparison lemmas, which always rely that the density, at least that's my understanding, that the densities are bounded away from zero and infinity, whereas here, you know, we can take any measures. So it's helpful in that direction. Since my time is close to getting over, I spare discussing what we get, which kind of large-scale linearization we get here, and perhaps I'm telling you just in the remaining couple of minutes a bit more about how to get this harmonic approximation result. I mean, I've told you how to construct the harmonic function phi, but perhaps I can tell you a little bit what's involved in the proof. And in fact, that is already non-trivial, but best seen in the case where the two measures are locally constant. So locally, the Lebesgue measure in some ball, that's still kind of a non-trivial situation and allows to kind of make the statements clearer. And that was what Michael Goldman and I started with. So again, we look at the solution of the Poisson problem. In this case, we can really take zero as the right-hand side with flux bound with Neumann boundary data, where the F bar is given by the time average of the normal component of J. And the statement is that the Dirichlet energy, that's the less important part of the statement, is the Dirichlet energy of this harmonic function is estimated by the energy of optimum transportation. But the more important statement is again that the transport velocity, the ratio of J and rho can be approximated by grad phi in the sense here. And the crucial thing here is the fact that this is a super quadratic approximation, that this exponent here is strictly larger than 1. And in fact, it comes out in a very explicit way from some isoperimetric principle. And in a certain sense, this statement reflects that for densities close to 1, the Wasserstein distance is not so different from the h-1 distance, something which Cédric Villani and I kind of remarked a long time ago. And so, so that's really kind of in the simplest version of this harmonic approximation result. And so here it is stated again, or the most important part is stated again, kind of this estimate here with this exponent strictly larger than 1. And so, so it proceeds in kind of 3 ways. First, you have to construct phi. I already told you how to do it by solving this this Poisson problem. Then you have to use something which is kind of an orthogonality property, which we know very well from quadratic variational problems, which tell you that the square of the distance between the minimizer and a competitor is controlled by the difference in their energies. That's always true for a quadratic variational problem. And it remains true, at least not as an identity, but as an inequality for the variational problem at hand. So, so this quantity here, which is the distance between the actual minimizer rho, J rho, and the competitor, is estimated by the difference in the energy of the actual minimizers and the energy of the competitor. But here you change problems, right, from nonlinear to linear, or from non-enharmonic to quadratic. And that, in this special case, is a nice consequence of McCann's displacement convexity, which ensures that rho is always less or equal to 1. And then you have to do something. You have to construct a competitor. You have to, based on grad phi, you have to construct a rho tilde J tilde, so that which solves the optimal transportation problem, so that its energy is controlled by the Dirichlet energy plus a little bit with the exponent larger than 1. And that essentially requires a boundary layer construction, because the mismatch between the optimal transportation side and the Poisson side is really that on the Poisson side you have averaged over your boundary flux. So you have to kind of accommodate the difference between the time averaged boundary flux and the non-time averaged boundary flux, and that requires a boundary layer construction. And the estimate of it follows from kind of, if you want, an isoperimetric estimate, some kind of trace type of estimate, and that brings in these exponents in the end. So that's the idea. And like in minimal surfaces, there is this isoperimetric principle which comes in, kind of lower dimensional isoperimetric principle. In fact, there is quite a number of analogies between, as I mentioned in the beginning, the regularity theory for minimal surfaces, for instance, as it was developed by Schön and Simon, and what we're doing here. And this slide, but I think I'm running out of time, accounts for this high level of analogy between the two approaches. Okay, so I think I'm out of time. There are a bit more details, so let me summarize. So so in a certain sense, the talk was an excuse to talk about optimal transportation, and what I told you about is a variational way of carrying out a regularity theory, and where the key kind of the key tool, the machine room is a harmonic approximation, and in a certain sense, this harmonic approximation is very natural from the point of view of optimal transportation, in particular in its Eulerian and its Benamou-Brenier formulation, and it allows to reprove, perhaps in a slightly sharper way, some of the results which have been around with the other methods, in particular boundary regularity. Recently, we generalized it to general cost functions, but it also, I guess, allows to do new things. And I just vaguely touched upon this, like this matching problem, which was kind of rediscovered by PISA physicists and then was taken over by PISA analysts. And I think that's an interesting problem, and that's where we want to make more progress in the future with Martin Hußmann and Michael Goldman. And I think I should stop because I'm kind of used up my 45 minutes.